Now let's find some limits. So let's take a look at this first one here. Now, because you guys are used to only two-dimensional limits here, in the last video I talked about all the different possible paths we can take for any one of these limits, which would become super overwhelming for us to think about, all of them in general. So we don't. We usually try to find some algebraic approach to actually do these problems. Now, taking a look at this, some of you might look at this and say, hey, just plug them in. And then if you plug them in, notice what happens here. I'm just going to show you what happens with that. So I'm going to get a 1 for the y, so that's going to be a 1 squared. Sine of 0 over 0, and I end up with 0 over 0. And then some of you might say, hey, we can use L'Hopital's rule. And I'll tell you, no, you can't. You can't use L'Hopital's rule here because it doesn't work for these two variables. So what we have to do is we have to take a different approach on this. So we have to be more creative. So remember in the last video when I talked about the different statements that hold here for the different properties for limits. And the condition was that the limit had to exist for both of the functions individually. So what that means for us here is that is there a way I could split this or in some sort of sum, difference, pull a C out, anything like any of those properties that would help me. And if I notice this product law might be able to help. And that's what we're going to try here. So I'm going to try to break this into two functions and times together, but both of those functions individually, when I take the limit, as xy goes to 0, 1, would have to exist. That means they go to some finite number. So that's what we're going to try here. All right, so this is going to equal the limit of xy. Now, if one of them turns out to be infinity or does not exist, then I can't use this process. That's the thing. I always try to plug in first, though, like I did in the beginning. And since that got me 0 over 0, got me 0 on the bottom, really, is what the problem was, then I couldn't do it. So I'm going to try to split this up this way. And then I'm going to say times. And then the other one is going to be the limit as y goes to 0, 1. And of the sine of x over x. Now, those are the two I'm going to break it into. Now, if you look at those, I split the x's and the y's by product, which was okay. I didn't violate any rules there. Now, again, if one of these limits gives me infinity or does not exist, then this whole process doesn't work for me. Okay, so keep that in mind. So now, since we separate it by the x and the y's like that, we can maybe talk about just the limit as y goes to 1, I should say, of y squared. And the other limit is really the limit as x goes to 0 of the sine of x over x. Now, again, like I said, if one of these limits gives me infinity or does not exist, then this whole process, I got to start and do something else. All right, so anyway, so we're going to take that first limit here, and I'm just going to look at that limit of as y goes to 1 of y squared. And that's a polynomial, and since I'm going to 1, it just equals 1 squared, which equals 1. So that limit does exist, and it's a finite number. So that's good. Hopefully we get the same thing with the other limit. So now we're going to do the other limit. So the limit as x goes to 0 of the sine of x over x. And when we plug it in, just like we did for the top one there, I'm going to get sine of 0 over 0, which is 0 over 0, which is grounds for L'Hopital's rule. And I can use it here because I only have one variable instead of two. So this is where it works. So remember, L'Hopital's rule says that if I get 0 over 0 or infinity over infinity, that the limit of my original function is the same as if I take the limit of the derivative of the top over the derivative of the bottom. So that means this would end up being cosine of x now on top, because the derivative of sine of x is cosine of x. And the derivative of x is 1. So now, when I plug in my 0 here, let's try it again. The cosine of 0 is actually 1. So my limit here is going to be 1. So now the huge benefit here of breaking this apart this way is now, since those limits were both finite, their product of the limits is equal to the limits, the finite numbers I came up with, the product of those, their actual limits, I should say. All right, so this is really 1 times 1, which equals 1. So the answer to number A is 1. So very nice when I can split those apart that way. Now looking at number B, that's not as nice. But let's see if we have to worry about it. Let's just plug everything in first and see what we get. Okay, so my x is 2 minus 1 minus 1. And on the bottom, I get the square root of 2 minus 1 minus 1. So on the top, I'm going to get 0. And this here, 2 minus 1 is 1. Square root of 1 is 1. And then 1 minus 1 is 0. So I get 0 on the bottom. So now, the first thing I would think of was L'Hopital's rule. But again, I have more than one variable, so I can't use L'Hopital's rule. So get that down. The faster you get that down, the better you'll be off with these. So we can't use that rule. This one, I have to be a little bit more fancy. Because when I start to look at all my properties, you'll see that none of them are really going to apply for us here. And that's kind of the sad thing. With all this power here, it's not going to be helpful. So what we're going to do for this one is I'm going to multiply. I'm just going to use some algebra here to try to simplify this a little so that I can get a really good limit here. So what I'm going to do is I'm going to take the top and the bottom and multiply it by the square root of x minus 1 plus 1. What I'm thinking here is the difference of squares. And this is actually going to help us with this problem. And I use the plus here because I'm thinking of, like I said, the difference of squares there, because I want to get rid of that square root on the bottom. And this is going to help us immensely here, believe it or not. Okay, I know it's going to look more complicated initially, but it's definitely going to help. Anytime I get a 0 on the bottom, I got to go through some sort of other process if the limit exists. Now, sometimes we'll get a limit that doesn't exist, and then we got to be even a little more fancy once we figure that out. And that might take some time to even figure that out, going through some of these algebraic processes. Sometimes it gets complicated. So anyways, what we're going to get on the top is, so for the bottom, since it's a difference of squares, I'm just going to take the first two and square them. And that's going to get me an x minus y, because the square root of x minus y squared is going to be x minus y. And then the minus here, and then the last one squared. So it's going to be a 1. Which, if you notice, that whole thing is the same as one of those factors on top. So they actually cancel out. And that's what's one of the fancy tricks for these. One of those algebraic tricks. So then this is going to equal the limit as xy goes to 2, 1 of the square root of x minus y plus 1. And when I take that limit, that's actually going to equal 2, because now I can just plug it in, because that's going to be a 2 there. That's going to be a 2. That's going to be a 1. So that's going to be a square root of 1. So I'll write that out. Square root of 1 plus 1. So square root of 1 is 1. So that's going to actually give me 2. So the limit for the second one is going to be 2. And again, keep in mind that did get a little more complicated to begin with. Anytime I see those square roots like that, though, on the bottom, that's where my mind goes right away. And I do think they exist right away, too. And that could be a problem later on sometimes if I'm given one that's not. But a lot of times that's what you'll see when you deal with those square roots.